Hi again. We are going to now derive the third equation, and I guess it's the same thing we are doing once again, because we are going to derive the third equation of motion through graphical method, and this is the graph which we have done before, and we are assuming that an object is traveling from A to B with a uniform kind of acceleration, but there is a change in velocity. And in order to derive the v part, we got the first equation, that is v is equal to u plus at. Now the second one, this particular object, that is car, when it is traveling from A to B with a uniform acceleration, it is covering some amount of displacement. And we assume that when the object moves from here to there, the displacement is somewhat approximately equal to the area of this diagram over here. So with this we got the second equation. Now we are going to continue from that part here, same thing. Position time relationship. Now in this case it has changed a little. This is not position time, but instead of writing position time, what we are going to write is we are going to write position velocity. Position velocity relationship. So again, this displacement is equal to the area of the trapezium. So now what is the area of the trapezium? S is equal to area of the trapezium is equal to half base 1 plus base 2 into height. Is that clear? Half base 1 into base 2 plus height. Now if you look at this one here, I think it will be a little difficult for you to imagine from this part. So let us take this example once again here. This diagram, this is the graph, same graph which I'm using it before, right? So now this is the trapezium here. Half base 1 plus base 2 into height. So let us take like this here. This is the trapezium. Half base 1 plus base 2. What is base 1? That is V is equal to half V plus. What is base 2? This is base 2 on top here. That is U. What is height? This is not the height. This is the height. What is height? T. And we are going to keep this as equation number 1. Again we are going to use the, equation of the acceleration, right? Through acceleration, A is equal to V minus U upon T. This is the formula which we knew it already, right? So now in this case, what I'm going to do is that I'm going to shuffle the A and T. I'm going to send this A down here, and I'm going to send this T on top here. That means I can write T is equal to V minus U upon A. Is that clear? Now, can you see there is one singular T here? Right? Instead of writing this singular T, we can write V minus U upon A. Why? Because this T is also equal to V minus U upon A. So what I'm going to do is that substituting T is equal to V minus U upon A in equation number 1. Right? So now I'm going to copy this equation once again. S is equal to half V plus U T. Now instead of writing T, I have to write V minus U upon A. So how am I going to write? This 2 I'm going to keep it below the V plus U. V plus U upon 2 into V minus U upon A. Okay. Now that sounds quite familiar here. Now I guess, do you remember one mathematical formula where you get something like this here? Do you get this equation? A square minus B square is equal to A plus B, A minus B. Now in this case, keep A as V. v plus u, v minus u. Is it saying a plus b, a minus b? So instead of writing v plus u and v minus u, can I write v square minus u square like this one over here? I can also write the same thing here. So how I'm going to write here? S is equal to v square minus u square divided by 2a. I'm going to write like this here. I got this now. Is that clear? So now I will write this portion over here. We got this here. S is equal to v square minus u square divided by 2a. This 2a I can multiply this one over here. So I'll get 2as is equal to v square minus u square. Understand? Which we can also write as v square. This is the third equation of motion through graphical method. And all these three equations are very, very important. So please do follow it, and if possible try to make notes of that. So when you write, you will try to understand far more better. That's all. Thank you. Tashit Ali once again. So I'm going to continue from the part where we had left yesterday. So yesterday we were discussing about these three equations here. This three equation is what we call as the equation of motions, with the object with a uniform kind of acceleration traveling in a straight kind of line. Now these are the three equations over here. Equation number 1, v is equal to u plus at, and the second equation, s is equal to ut plus half at square, and the third one is v square minus u square is equal to 2as. So now today I brought three kind of questions here. First, the question with the yellow one, I'm going to use this formula here, v is equal to u plus at, to solve this. And the second one, a train with 36 kilometers, that second question with this formula here. And the third one, that blue with the blue kind of formula here, right? So let us proceed with the first one, and I'm going to solve with the yellow chalk here. Okay, so the solution here, I'm going to write it. Whenever you are trying to solve any kind of question, I think it's very important for you to understand first thing the question itself, right? So here, starting from a stationary position here, stationary position means that object is not moving before. So we can somehow indicate that u is 0. Understand? U is 0 meter per second. Why? Because this object is in a stationary position. And what is that object? That object is a car. Now it moves to attain a velocity of 72 km per hour. That means now there are two different kind of velocity, and the velocity number 1 is initial velocity, that is u, and the 2 is final velocity, that is v here. Now I'm going to write the equation here. V is equal to u plus at. We got this u, that is 0 meter per second. Now this car, it moves to attain a velocity of 72 km per hour. That is the v. Now here, v is 72 km per hour. But 72 km per hour is our not standard international unit. So we have to convert that into the simpler terms here. So how we are going to do that? 72 into, in 1 kilometer there is 1000 meters. There are 1000 meters here. 1000 hour. In 1 hour, how many minutes? 60 minutes. In 1 minute, how many seconds? 60 seconds. So when you multiply these two, what you will get? 72 into 1000 divided by 3600. So please keep that in your mind. Whenever you are converting kilometer per hour into meter per second, you always have to multiply by 1000 and divide by 3600. So now let us calculate. 0 and 0 cancel out. 36 ones are 36, 36 2s are 72, right? So 2 10s are 20 now. Now this is our final velocity, that is v is 20 meter per second. We got this. Now we came over here. In a time interval of in 10 seconds. What is second? Second is a time. So now the third one is t is 10 seconds. We got this, right? Now, calculate the acceleration of the car. That means we have to find this. So now we are going to find this, okay? Now, we are going to write the formula V is equal to U plus AT. This plus sign, I'm going to put that on this side here. So I will get V minus U is equal to AT. This T I'm going to send down here. V minus U upon T is the formula of acceleration, which we know it, right? So how much is V? Is 20. And how much is U? 0. How much is time? 10. How much is acceleration? We don't know it, right? 20 minus 0 is 20. Divided by 10 is 10 ones are 10. 10 twos are 20. That is 2 meter per second square is the unit of the acceleration. This is how we solve the first calculation of the equation of motion. Understand? Let us go for the next one. Okay, now this time with this chalk here, that is a red or whatever it may be, purple kind of chalk here. Again, solution we are going to write. A train with 36 km per hour velocity covers a distance with a uniform acceleration of 2 meters per second square. Now in this case, we have given you only one kind of velocity here, that is 36 km per hour. Because we didn't say that this train is coming from a railway station. Let's suppose, imagine if this train is coming from a railway station, then in the railway station, its initial velocity is 0. But over here, this train, in this case, you can make out only one kind of velocity, and so we are going to take this as U here. So now, S is equal to, we are going to use this formula here, UT plus half AT square. Right? So, now we are going to take the U, that is the velocity, is 36 km per hour. 36 km per hour. So, whenever we are converting kilometer per hour, what we have to do, we have to multiply by 1000 and divide by 3600 here. 36 into 1000 divided by 3600. Why 1000? Because in 1 kilometer there is 1000 meter. Why 3600? Because in 1 hour there are 3600 seconds. So we are going to cancel it. 0, 0 cancel. 36 1, 36 1. What we are left? 10. That is 10 meters per second. That is U. Right? Now we got the U with the velocity covers the distance with a uniform acceleration. Okay, they have given the uniform acceleration. That means we got A is equal to 2 meters per second square. Understand? So now we got this, and we got this. Right? In a time interval of 5 seconds now. How much is the time? Is 5 seconds. Time we got. Calculate the distance traveled by the train. Now we have to find the distance here, right? So S is equal to UT plus half AT square. How much is U? 10. How much is time? 5. Plus half into how much is acceleration? 2 into how much is time? 5. Don't forget this. Many of the students, they tend to forget about this square, right? So 5 times are 50 plus this 2 we can cancel it. 5 5s are 25. So when you sum up this 2, you will get 75 meters. This is your answer. Understand? Is that clear? Okay. Now we will go for the third one. Okay, so the third one is the formula V square minus U square is equal to 2AS. Again, we are going to write the solution as this. Now, we are going to write, a car is traveling at a velocity of 10 meters per second. That means a car is already traveling at an accelerated velocity of 10 meters per second. Now we have to understand, brakes are applied so as to produce a uniform acceleration of 0.5 meter per second. Now it's very confusing over here, this part here. So let us forget about this for the time being. So what a car is traveling at a velocity of 10 meter per second, brakes are applied so as to produce a uniform acceleration. We're going to write A is equal to minus 0.5 meter per second square. This we are going to make up. Find how far the train will go, right? So this acceleration we got. Now we need V and U. Understand? So now we have to understand which one is U and which one is V, right? Okay. So now a car is traveling at a velocity of 10 meter per second. Now try to understand the situation here. This car is traveling already. When you apply the brake, the car will stop. So what is the final velocity? 0. Let us suppose imagine this is a car. 10 meter per second. Suddenly brakes are applied. It stops here. Now that is the 10 meter per second is the initial velocity. When the brakes are applied, it stops. That is the final velocity, which is equal to 0 meter per second. So how we are going to write here? U is equal to 10 meter per second. And how much is the V? V is equal to 0 meter per second. Is that clear? I hope you are not confused in that, right? Okay. So now by using this, we got this. We have to find how far this particular distance we have to find. So we are going to use this now. Okay. So V square minus U square is equal to 2AS. How much is V? That is 0 square minus how much is U? 10 square is equal to 2 into how much is the acceleration? Minus 0.5. I'm really sorry. I will write it more smaller. Okay. 0 square minus 10 square is equal to 2 into minus 0.5 into S. Understand? Here. So now when you subtract this, 10 times are 100. 0 square 0. When you subtract it, this is greater, so we are going to write minus 100 because 10 square is minus 100 equal to 0.5 into 2 is 1, that is minus 1 into S, right? So now you can cancel this out. This 1 doesn't have any kind of value in general, so we are going to write your 100 meter is equal to S. This is your answer. Understand? Is that clear? So this is how we are, solving, even though there are so many different kind of like calculations in your science textbook, and it is not at all possible for me to cover all the calculations because it normally takes a lot of time in that. So now coming to the last topic of this chapter, that is motion, that is uniform circular motion, right? Okay, let's go for it. It will not take that much amount of time. So talking in terms of uniform circular motion here, uniform circular motion. Uniform circular motion. If any kind of object, let's say this is the satellite here, which is high up in the sky. If any kind of object moves in a circular pattern here, with a uniform kind of speed. Uniform speed means, suppose imagine over here, if this particular satellite is traveling with 10 meter per second, it should be traveling 10 meter per second over here and over here. At every corner, this is 10 meter per second. If any kind of like object which moves with a uniform kind of like speed in a circular pattern is what we used to call as uniform circular motion. Now, generally speaking, let's say we used to ask conceptual questions like, let's suppose imagine, okay, this is the satellite and this is revolving around the earth, right? Suppose imagine if all of a sudden, okay, this satellite is connected to the Earth. Let's suppose, imagine, okay, if we are going to break this part here, break the link between these two, what will happen to the satellite, in which direction it will go, right? For example, okay, we normally have this kind of thing here. There is a rock and there's a string here. This rock begins to move in a circular pattern here. Now all of a sudden, if we cut this rope on the process, when we were circulating it, this rock, when the moment it reaches over here, in which direction it will go? This was the commonly asked conceptual question, where it will go. So the point is, if I am going to cut this rope, when the rock is over here in motion, this rock will go in a tangent way. We used to say, there's a mathematical term, tangent. Tangent normally means a line which is, this is a line which is touching the circle, right? Suppose, imagine if I cut the rope, the string, when the rock is over here, it will go in this pattern here, circular. Over here, it will go in this kind of pattern here. Understand? So this is just about the uniform circular motion. So with this, I came to the end of this chapter on motion. So I shall see you later, and I hope all of you must be having a little amount of understanding regarding what I had taught till now. So thank you very much, all of you, for listening so well. And I tried my level best, even though it's quite difficult for me to get all the resources during this lockdown period. So I had to go for the chalk and blackboard, which is my best friend. Okay, so thank you very much, everyone, for listening so well. Thank you.